All right, let's dive right in. Today, we're going to crack the code on one of the most important ideas in all of chemistry, valence electrons. Seriously, we are about to uncover the secret that dictates how, well, literally everything in our world gets built.
You know, it all boils down to this one question. Have you ever wondered why something like sodium explodes when it hits water, but the neon gas in a glowing sign just sits there, doing nothing? What is the big difference? Well, the answer to that little mystery is what this is all about.
Okay, so to find that secret, we need to do a super quick refresh on what an atom is actually made of. Let's just get the basic ingredients down, and then we'll introduce the real key player here.
So picture this. Every single atom has a core, right? That's the nucleus. And inside, you've got your positive protons and your neutral neutrons. But honestly, the real action, the stuff we care about today, is happening with that third ingredient, the negatively charged electrons that are just zooming all around that nucleus.
Now, these electrons aren't just flying around in a chaotic mess. It's actually way more organized. Think of the nucleus like the center stage at a huge concert. The electrons are sitting in these perfectly defined rows, or shells, that go out from the center. The inner rows always fill up first, and then the next row, and so on. And here's the secret. It's the electrons in that very, very last row that matter most.
And that, right there, brings us to the star of our show. You could call them the secret agents of the atomic world. It is time to formally meet the valence electrons. And it's really that simple. When we talk about valence electrons, we are only talking about the electrons in the absolute last outermost shell of an atom. We ignore all the inner ones. They're just on the frontier. They're the face that the atom shows to the rest of the universe.
So why are we so obsessed with these specific electrons? Because they decide everything. I'm not kidding. They are the ultimate decision makers for how an atom is going to act. They control its whole personality. Is it going to be super reactive or super chill? Who is it going to bond with? What kind of molecules is it going to form? It's all up to them.
So what's driving all this? What's the motivation behind this behavior? It really just comes down to one single powerful goal that almost every atom shares: this deep, deep quest for stability.
Think of it this way. Atoms are kind of like people. They just want to feel happy, stable, and complete. And for an atom, that feeling of completeness happens when its outer shell of electrons is totally full. That is its ultimate life goal.
And what does full usually mean? Well, for most atoms we're going to talk about, the magic number is 8. This is so common it has a name, the octet rule. If an atom can just get to 8 valence electrons, it's like it's achieved chemical nirvana. It's stable, it's content, and it has no reason to react with anything anymore.
So here's the million-dollar question. How do they get to 8? I mean, if they don't have a full shell to begin with, they're going to do whatever it takes. And they've got 3 main moves. They can either ditch their extra electrons to clear out that shell. They can snatch an electron from some other atom to fill a gap. Or they can get cooperative and share electrons with a neighbor.
All right, that's enough theory. It makes a lot more sense when you see it happen. Let's look at a few really famous examples.
First up, let's look at sodium. It's got 11 electrons. They're arranged in shells with 2, then 8, and then this one lonely little electron all by itself in the outer shell. Now to get stable, what's easier? Trying to find 7 more electrons or just getting rid of that one? Yeah, it's way easier to just lose the one. And this makes sodium desperate to give away its valence electron, which is exactly why it's so ridiculously reactive.
And who's the perfect partner for a giver like sodium? Meet chlorine. It has 7 valence electrons. It is so close to that magic number 8. All it needs is one more to be complete. So chlorine is desperately trying to gain an electron, which makes it just as reactive as sodium, but for the total opposite reason.
And then you've got neon. Look at its outer shell. It's already got 8 electrons. It's already 1. It's stable. It's happy. It's got its full octet. So it has absolutely zero motivation to gain, lose, or share anything. This is why neon and other elements in its group called the noble gases are so unreactive. They're already living their best chemical life.
And these examples perfectly show the single most important rule in all of chemistry. Those inner electrons, they're totally shielded. They're just watching from the sidelines. All the real action, all the giving, the taking, and the sharing that creates the world is handled exclusively by the valence electrons. That's it.
So this whole dynamic leads to the 2 main ways atoms bond together.
When an atom like sodium literally gives its electron away to an atom like chlorine, we call that an ionic bond. It's a straight-up transfer. But sometimes atoms work together. For instance, two hydrogens and an oxygen will decide to share their valence electrons so everybody feels like they have a full shell. That's a covalent bond, and that's exactly what holds a water molecule together. Now you might be thinking, oh man, do I have to memorize the electron shells for every single element on the chart? And the answer is no, absolutely not, because there's been this amazing cheat sheet hiding in plain sight this whole time. And here it is. This is the big reveal. The periodic table isn't just some random collection of elements. Its entire structure is a code designed to tell you about valence electrons. It's basically a map of chemical personalities. Just look at this. It's so cool. For the main columns, the group number tells you exactly how many valence electrons an atom has. See group 1? Everything in there, like sodium, has 1. Jump over to group 17, where chlorine lives. They all have 7. And all the way on the right, group 18, the noble gases like neon, they all have 8. It's this beautiful, perfect pattern. So let's just boil this whole thing down to a simple chain of logic you can remember. Ready? Valence electrons are the outermost electrons. Because they're on the outside, they're the only ones that do the bonding. And since bonding is just another word for chemical reactions, these electrons drive all of chemistry. Simple as that.
So here are the big ideas to walk away with. Why do valence electrons matter so much? Because they are the ultimate puppet masters of the chemical world. They determine how reactive something is, they control every single chemical bond, and they're the tool atoms use to finally get stable and find peace.
So, the next time you look at anything, really, a grain of salt, a glass of water, the air that you're breathing, just remember what's really running the show. It's these tiny, tiny particles on the outer edge of atoms orchestrating this incredible chemical dance that builds our entire reality. That's the amazing power of valence electrons.